Hello and good morning, everyone. Hope you're all having a fantastic morning. First of all, I would like to thank you for taking the time to join us today on our webinar. I can see that people are already joining, so please, if it's the first time you join, introduce yourself in the chat window. Tell us your name, where you're listening from. Hello, Mario. Good morning, Shai. We have also Kiwei from Singapore. Hello. See some familiar names and also some new names. That's always interesting. Hope you have your coffees ready. I'm just waiting a minute for the rest of the people to join so that we can start all together. We have Terje from Norway. Hello, Terje. Okay, so what are we going to be speaking about today? Well, first of all, my name is Omar. I am the applications engineer at Radiocrafts. And today we will be discussing a very interesting topic of comparing RIIM, which is our solution, to other technologies. And don't worry, we will not just be going through all the metrics and saying RIIM is better than everything else. No, we will have another approach to that. But first of all, let's go through some ground rules together. This webinar, we'll try to keep it short and simple, so it will be scheduled for around 30 minutes. We will have at the end a small Q&A session of around 10 to 15 minutes. So please, while I'm speaking, if you feel you have any question, leave it in the chat window. And you'll get back to it at the end of the presentation. Not finished here. And as usual, after the presentation is over, we will post a recorded version of the webinar on our website in case you want to go through that again, in case it was very interesting maybe. And anyways, please feel free to visit our website and register to our document library to gain access to, I would say, hundreds of very interesting detailed white papers and app notes and user manuals and quick starts. All right, I think now everyone is more or less here. Coffee's ready, and let's go. So what do we have in the agenda? It's a pretty meaty presentation, but I'll try to keep it simple as possible. We will discuss first that now there is a huge variety of RF technologies to enabling IoT. Then we will speak about how to differentiate between these different technologies, because when you have a huge variety of technologies, you might get confused, you might get lost, you might want to know how to think and how to approach it and how to choose, how to select the right technology for you. Then we will go briefly through some of the trade-offs that RF technologies have to do sometimes to achieve a certain metric over and sacrifice the other. And at the end, we will finish this presentation by presenting a brief kind of comparison between RIIM and some of the common RF technologies now in the market. Well, first of all, this is not me, no. I'm the handsome guy who was in the previous slide. Anyways. So what is IoT? Of course, you all know, but very briefly, IoT connects an ecosystem of sensors and devices to a network. But maybe the story from the beginning is that when they wanted to find the best RF enabler for IoT, they thought, okay, what are the key characteristics of IoT? Does IoT require long range, low power? So they turned to the existing technologies at the time. Remember, that's not now, that's a little bit in the past. So they thought, okay, what do we have now? They have Zigbee and they have maybe Bluetooth. But then Zigbee and Bluetooth, they actually had very short range. So they thought, okay, if we want longer range, what about we turn to cellular technologies? But of course, for IT, this would never work because cellular technology, at least the legacy cellular technologies, as they were in the past, they consume very, very high battery. Therefore, the requirements for IoT, they kind of drove the development of a new category of networks, a new category of RF enablers. And they created their own category called LPWANs, or low power wide area networks. So briefly, we have now the group of cellular technologies where we have specifically made technologies which are made for IoT use. They're different from the cellular that we use when we speak on the phone, such as narrowband IoT and LTE category M1. And then if you look at low power wide area network networks in the star topology, you have Radiocrafts Riot, you have LoRaWAN, you have MBus, MIoT, the infamous Sigfox. Then also in the mesh topology, you have RIIM, WirePass, also Zigbee mesh. It's very popular. Then, of course, you have the usual local area networks like Wi-Fi. But the local area networks like Wi-Fi, they have very huge power consumption, so they will not be in the scope of at least this discussion. So, as we saw, we have a huge variety of options, tons of things to choose from. So how can we do that? Well, the best way to deal with this is by differentiating between them. We will group them into certain categories according to certain traits that they have. Then we can compare between them. So the first aspect that we will use to differentiate is the topology. As you see in the mesh architecture to the left, we can see the most common examples of mesh networks, like Radiocrafts RIIM, you have Zigbee mesh, WirePass, and so on. While on the right-hand side, and arranged in the star topology, you can see some of the most common star topology networks, like WISE, MIoT, and of course, LoRaWAN. All right, so now I know which are arranged in a star formation and which are arranged as a mesh. But what does that tell me? What should I choose? Well, this totally depends on what you want. Both categories have their own pros and cons, and all you have to do is to see which pros you care about the most and which cons do you not mind losing to achieve those pros. Let's say, for example, mesh networks, they allow for extended range. And due to their mesh structure, they allow for multiple routes, which gives reliability. But does this come for free? Is this like a magic solution? Not really, because this also comes on the expense of the added latency and the added overhead traffic. Because all these network maintenance packets, they consume RF resources. All right, so let's see on the other hand. You have star networks, which come with advantages such as simplicity, as each node is just connected to the gateway via one link, and that's it. No mesh structure, no complexity. Well, is that also perfect? Not really, because this comes on the expense of quality of service. Since there is not much room in star networks for acknowledgements and retransmissions, then there's less probability of detecting when there is a lost transmission. And of course, the core of a star formation is that the gateway is in the middle, connected by one link to all nodes. And this kind of star formation, it has a very critical issue, which is it has a single point of failure, which is the gateway. While in a mesh topology, if a mesh router fails, the topology will always reorganize itself and heal itself to find a new path. So here you have to ask yourself, do I need to cover hard to reach places? So I need the extended range abilities of a mesh network? Am I worried about network congestion? So maybe mesh is not the best for me. Okay, so that was the differentiation in terms of topology. Now let's have a look on how it is to differentiate between different RF technologies on the basis of the operating frequency they operate on. Here in the x-axis, we have the frequency band, like the most common used frequency bands. On the lowest side, on the left, we have the 169 megahertz WISE protocol. We have also in the middle the 433 megahertz WISE MBUS. Then we have the 868, which is the license-free in Europe and also in other places, where we have famous examples like wireless MBUS and RIIM and Riot, LoRaWAN, etc. 915, which is most commonly used maybe in Australia, New Zealand, where you have YSAN, Sigfox, MIOT, and kind of the same. Then on the right-hand side, on the higher frequency range, you have the 2.4 gigahertz solutions, such as Zigbee Mesh, Bluetooth Mesh, and WirePass, and so on. Okay, so now I know which technology operates where. What does that mean? How does that help me? All right, so this dotted line in the middle, it represents the 1 gigahertz, let's say, differentiating point. The right-hand side is the 2.4 gigahertz group, and the part on the left is commonly called the sub-1 gigahertz family of technologies. In the sub-1 gigahertz part, where frequencies are relatively lower, this gives huge advantages. First of all, your path loss increases with the increase of frequency. So when you go sub-1 gigahertz towards lower frequencies, you have less path loss. You also have the fact that lower frequencies tend to penetrate walls better. And not only walls, it may be also vegetation in the street, obstacles, and so on. So we have the sub-1 gigahertz group, which have its most critical advantage is penetration and better signal propagation. Of course, that doesn't come without a price, because to increase the range, you have to also decrease the data rate. When you operate on narrower channel bandwidth, you have less data throughput. That's the price you pay. While on the other hand, if you go towards the 2.4 gigahertz, you have wider channels, you have higher data rates. You can reach data rates of 1 megabit per second and even much longer, much more. And also you have the advantage that the more the frequency is, the smaller the antenna will be. And this is more suitable for in-home applications, since it's not really pleasant to have a big antenna device in your living room. And also you have the advantage that in most places in the world, the 2.4 gigahertz band is kind of the unlicensed band. Most Wi-Fi routers use it. It's unlicensed, it's free. So this is a huge advantage, that you can have just one solution that would work anywhere, kind of a global unified solution. But what's the downside of the 2.4 gigahertz technologies? Of course, range. Because roughly, and in optimal conditions, without accounting for anything more, just physics, when you double the frequency, you have the range. And of course, you have the other advantage, the other disadvantage, which was an advantage before, is that on 2.4, everything's working and you have the unlicensed band, and this has support for everything. But at the same time, this will create interference, since you will have nearby Wi-Fi networks and so on. Okay, so what does that mean? It means that if you go sub-1 gigahertz and star technologies, you have the low power wide area networks, also known as LPWANs. And these, they have the advantage of the increased range per hop, since it's star and it's sub-1 gigahertz. While if you go still sub 1 gigahertz, but you go mesh, you have the famous RIIM, you have Wi-SUN, etc. And these have the advantage of the increased overall range since they are mesh networks. Of course, in the 2.4 and star, you have BLE, and then in the mesh and 2.4, you have WirePass and Zigbee mesh and Bluetooth mesh, etc. All right, so we differentiated between different RF technologies by topology, differentiated by operating frequency. Now let's see about range and coverage. There is always this endless bidding war between marketing departments of different companies to promote higher range. But can range actually be compared this easily? And how do LP1s achieve high ranges? Well, first, LP1s strive on sacrificing data rate to favor range because they know that wireless sensor networks don't need that much data rate. So they sacrifice data rate to increase the receiver sensitivity and thus increase the range. All this, of course, while trying to keep battery consumption at bay. On the other hand, mesh networks use their mesh advantage to easily extend their inherently shorter one-hop range. But here comes the issue. How can you compare the high range of a star network to the shorter but extendable mesh node range? We always have to keep this in mind because it's not only about the number that this star network has this X meters of range and then this mesh has this Y number of meters covered, because you can't compare them because this is star, this is mesh. With mesh, even if you have a shorter range per hop, you will always have the advantage of just adding a mesh router and achieving coverage there. While with star, you don't have that, but you have the more range per hop. There's also another thing, that ranges hugely depends on many things. Like the same product can be measured its range by two people, but then having different results. Maybe the two people are in different parts of the world. Maybe they had different antenna positions. Maybe the transmitter and the receiver were on the ground, and in the other example, they were on mountaintops. Maybe the test was done in the city and the other was outside of the city. Numerous factors actually affect the range, but in general, you can say that the 2.4 mesh, like Zigbee mesh, for example, would achieve an open field range of 150 meters, while indoor it would be maybe 10 meters square. A mesh like RIIM, working on the sub 1 gigahertz, would have an open field range of 500 meters, while having only 25 in the indoor. Still with RIIM, if we check RIIM high power, you can go, since it's sub 1 gigahertz and it's high power, you can go up to more than 5, maybe 10 kilometers with the line of sight. And then, of course, you have LP1s, which have the advantage of the very long range one hop, which can achieve more than 10 kilometers, at least theoretically. Another way to see differences between different RF enablers is the system ownership. Is this network going to be owned solely by me, or am I actually subscribing to an already existing ecosystem? A couple of the most famous public or shared networks is Sigfox and maybe narrowband IT. These are maybe the most famous couple. And there you actually have to subscribe to an already existing network. Like for narrowband IT, since it's a cellular, you need to buy a SIM card and insert it in your device and so on. On the other hand, private networks are the ones you own and have full control of, such as Radiocrafts, RIIM, and RIIT, for example. LoRaWAN is kind of in the middle since it supports both modes. Okay, so again, we know now which is public, which is private, which is public, but what does that mean for me? Well, with the private, you have the, since it's yours, you have the pros that it has more security, it has more longevity in the meaning that, for example, if you have cellular technology, it might be rolled back at any time if there is a newer technology being rolled out. This means they have to change everything. But when it's yours, it's your private, then this will never happen. But of course, since you have to do everything, so it's your responsibility, it's more complex to set up, and it's managed by you. While in the public, you have the advantages that it's more simple, it's managed by the provider, so no effort from you on that. But of course, the total cost of ownership is higher because it requires subscription fees. As we were discussing, sometimes RF technologies have to do some trade-offs or sacrifices to favor one metric over the other. One of the most famous couple in this sacrifice or trade-off is the quality of service and the battery lifetime. As we see this vicious cycle, let's say we have a star network which has an overall short RF range. So they have to, and to keep the battery consumption low, then they have to fix that by lowering the data rate. And since the gateway can't listen and transmit simultaneously in star networks, then this means that you don't have much room for downlink, which consequently means that you don't have much room for acknowledgements, which again means that this gives higher probability of failed transmissions going unnoticed, since the sensor device can't make sure that the gateway heard its transmission. There's no acknowledgement, so it can't know that. And of course, when you have a higher probability of failed transmissions going unnoticed, you would have less reliability, which means lower quality of service. So to keep battery lifetime high and to keep the power consumption low, quality of service sometimes has to be compromised. So here again comes the question: what do you need for your own use case? Do you is it something mains powered, so you don't care about battery consumption, but you care much about maximizing the quality of service, or is it the opposite? Mesh networks, they have high data rates. When they have high data rates, they can implement ACKs and retransmissions. So does this mean that they have higher quality of service in general, and is this perfection? Not really, because the ability to retransmit packets means more battery consumption. So the moral of the story would be that you might have to sacrifice some battery lifetime for higher QoS, and of course the opposite. Then some common LPWANs, they compensate because they have to deal with it. So they have to keep battery consumption low, but still they don't want to sacrifice QoS totally. So then to compensate for that, like for example, Sigfox allows for 3 retransmissions, LoRa uses FAC coding, MIUT uses a number of different techniques. It uses very advanced FEC, forward error correction. It uses also some sort of TDMA and FMA, FDMA and TDMA to ensure that the message is transmitted on different frequencies at different times to ensure that the message is not corrupted and it reaches the intended receiver. So maybe MIUT, since it's the newest, is the kind of the most advanced in this aspect, compensating for the lower quality of service. Another couple of trade-offs, which is actually very interesting, is the range and the data rate. Since LPWANs, they favor increased range, they do this because no sensor reading with application would actually need 0.5 megabits per second and any bigger than that. But actually, this decreased data rate means more time on air, since you have to spend more time with the radio on to send the same packet size, which increases your duty cycle usage and also increases battery consumption. So again, the moral of the story is that while sacrificing some data rate to increase range, it still also affects battery lifetime. So we always have to keep these things in mind when thinking about the best RF technology for our certain use case. Okay, so speaking about battery lifetime comparison, it's not easy actually to compare between different technologies with terms of battery consumption, since everyone has specific data rate. Each one has its own packet size. Each one has its own sleep time, sleep current. So it's not easy, but to try to keep it, to try to unify some rules. We have, for example, RIIM and RIIT. They use 50 kilobit per second, which means they take 4.8 milliseconds to send 30 bytes. And then this 125 milliamp times millisecond is if you assume that there are no acknowledgements, if you assume, and this is only for the TX current without sleep current, it's not calculated, to avoid thinking about how much the device sleeps, because it's different between different technologies. And we assume 30 bytes packets sent once per minute. We assume this for all technologies. So if we unify all these, of course, the numbers here are not realistic since we are assuming some unrealistic things, but if we unify them, they can be fair to compare. We have RIIM and RIIT with 55 years on of battery on 1,000 milliamp hour battery. You have Sigfox, which would give you maybe less. LoRaWAN also way less. MyOT would give a little bit less than RIIM and RIIT. Maybe the most battery would be achieved with the BLE and BLE long range, since they have the highest data rates. But if we look at it from outside, we would see that RIIM and RIIT are kind of in the middle. They are kind of balancing between data rate, sleep current, and packet size. Okay, so let's try to compare between RIIM and LoRaWAN. First of all, LoRaWAN has a bit special. It has some special parameters like spreading factor. Very briefly, the spreading factor, the higher it is, the highest is 12. It gives the lowest data rate, but it has the advantage that can be used under the worst SNR values, and it gives around 0.3 kilobit per second, while the lowest spreading factor, which is 7, gives the highest data rate, but of course, it can't be used unless the SNR is excellent. It gives around 27 kilobit per second, so you can see that LoRaWAN has a range of different data rates that can be used. And of course, when you use different spreading factors, this allows for highly dense networks. And as you can see, LoRaWAN is a living example of sacrificing data rate to extend the range. So how does how does LoRaWAN actually perform in open field, in field measurements in general? We have this diagram. It's taken from the research paper mentioned down here. So on the right-hand side, we have the, on the left-hand side, we have the line of sight range plotted against the packet reception ratio under 5 different spreading factors. And on the right-hand side, we have the same parameters plotted, but for non-line of sight. In the line of sight figure on the left, we can see that up till 5 kilometers, the packet reception ratio is acceptable. But as the distance between the transmitter and receiver goes beyond 5 kilometers, then severe degradation can be seen. Can even be seen across all spreading factors. You have to remember spreading factor 12 is the one that provides the least data rate. That's why it can theoretically reach 10 kilometers of range, since it gives the highest range. Of course, if you can tolerate the packet reception ratio. Then, of course, in figure B, the line of sight part, don't get tricked by how it looks, because the scale is not the same. On the right-hand side, the scale is still 7 kilometers. And you can see the even more severe degradation in packet reception rate at distances as short as even 1 kilometer. So how can we compare them? Well, they cannot really be compared in general, like abstractly compared. You have to compare them maybe in light of a specific use case. Because as you know, RIIM has mesh routers, but LoRa has longer distance in one hop. So you have to ask yourself, what does your use case need? Does it need the higher range per hop? Does it need better quality of service? Does it need less battery consumption, downlink, throughput, less latency? If we look in them in light of, for example, street lighting and smart irrigation, we can see that these applications might need some downlink for control, and in that aspect, RIIM is better. Power consumption, RIIM is better. Throughput, RIIM offers more throughput. Quality of service, RIIM is better. And when it comes to architecture, since RIIM is mesh, so for example, in street lighting, if you have a new building being built, if you have some sort of obstacle in the street which you can't control, which would affect your deployment, just adding a mesh router there would easily fix the issue. Does this mean that RIIM is the best solution ever under any circumstance in any use case? Not quite, because if you look at mass and dense deployments, they require less network overhead traffic. In that aspect, LoRa wins. You might need more than 1,000 nodes per one gateway. In that, LoRa wins. If you need to avoid routers to decrease expenses, here, LoRa wins. If you want more range per hop, then also that aspect, LoRa wins. So it's not easy to just compare directly, but when comparing in a specific use case, which has specific requirements, then it can be very easy to see which technology is the best. Okay, if we try to make it a bit closer and we say that, okay, let's compare RIIM to another mesh. All right, so we choose WirePass, for example. It's a 2.4 gigahertz mesh. So of course it has the advantage of global support. But of course, since RIIM is sub 1 gigahertz, it has more signal penetration and less interference. But maybe WirePass is more suitable for massive deployments, while RIIM is not. So again, here you have to ask, what does your use case dictate? Do you need tens of thousands of devices per network? If so, then WirePass is better. Do you need more range, more penetration? If you have some trees in the street, you need to have some good indoor coverage, then RIIM is better. And of course, you have the advantage that RIIM in the SDK 2.0 solved the duty cycle limitations by using adaptive frequency agility and listen before talk techniques. And we've already went through these advantages of RIIM and WirePass. Now, if you want to compare RIIM with other generic sub 1 gigahertz, such as Wi-Fi, Tiny Mesh, DG Mesh, etc. Okay, so if you want to just specify where does RIIM shine, where is the best cases to use RIIM, if you need battery-operated mesh routers, if you need time-synchronized nodes and channels, if you need higher duty cycle in Europe, since with RIIM you can reach almost 39% more duty cycle. If you need high power modules, which can transmit up to 500 milliwatts and reach over 10 kilometers in line of sight, it's an open standard, so not tied to a specific backend, and of course it's IP-based. Where I would not really advise you to use RIIM? If you need maybe very low latency, where any latency is not accepted, if you need more than 1,000 nodes in a network, if you need very high data rates, then maybe RIIM is not the best solution. All right, so just to summarize this quickly, what you wanted to say is that there's no one solution which is the best in general, no one solution which fits everything, because that's not even realistic in life. You always have to think about the use case and what its requirements are. And if you speak about RIIM, then of course you have a variety of features which make it very unique and places it, since it's sub 1 GHz and it's mesh, and it's all embedded in one module. There's no license fee, no subscription. You have time synchronized channels and duty cycles and so on. So RIIM is kind of a unique place, but in general, it all depends on your use case. So I am sorry that I took 6 minutes more of your time, but I hope that was helpful. I can see that we have some questions here. Will be helping me for the questions. We have also Rian, our R&D director in Radiocrafts.
Hello and good morning, everybody. Yes, I was asked to, so I can look at the questions while Umar is presenting. So I have, of course, seen the questions. So let's go through them from the start here. The output power we used in comparison. First of all, this range comparison wasn't like the max range. This was what I would have planned for if I was planning a network. So that means, for instance, 2.4 GHz or Zigbee. I know it can reach more than 150 meter outdoor, but I wouldn't plan for more in an outdoor environment. So the output power we used was the standard from the available chips. So it was 8 dBm on Zigbee, which is pretty much a standard Nordic type of, or BLE, standard Nordic chips for that, or TI chip for that, and 14 dBm for the sub 1 GHz. So it's basically based on the European. So we didn't add 27 dBm for Europe or any range extender for 2.4 GHz either. In the range in meter 2, that's of course not correct. It's meter. If it was meter squared, it was a typo. If maybe it was a footnote, because we had a footnote on that page, but it's definitely meters. So we have a question about reason not having room to do X in star technology. So yeah, I might have to elaborate a bit on that. So what we're talking about here is LPWAN star topologies. So that means that in like short range star technology, like wireless MBUS, like Riot, like BLE, you obviously can do acknowledgement. But when you do things like Sigfox or LoRaWAN with high spreading factor, you basically have very long packets, up to a second or maybe more than 1 second per packet. And that means that sending acknowledgement to packets also means that the gateway is busy for a very long time sending this acknowledgement. That gives two problems. One is the fact that we can, you get, when the gateway is transmitting an acknowledgement, it's not listening to other packets, so we will lose data. So they are deaf when they are sending. And the other is that, specifically in Europe, the gateway might easily become have a challenge with the duty cycle limitation of 1% or so, or maybe 10%, but still. So that's the second challenge you get by having that, and that's why the operators like Sigfox and operators of LoRaWAN public networks, they will not allow all devices to get acknowledgement. So there is limits how much you can do, because if you have 5,000 devices, then you start to get the issue if you do acknowledgement on all packet. Simply you get congestions in your network. And then Mario has a question on spreading factor data rate was used for the LoRa battery. That was the spreading factor 12, but that was also used for the range presentation of. So at least we used the same one for both when we compared to LoRa. How do we position Zeta LPWAN? To be honest, I know very little of Zeta LPWAN. It is, of course, a Japanese alliance, basically. I have not seen it a lot in Europe, to be honest. We have not heard customers having this competing or having this evaluating our solution towards LPWAN. But if it's an LPWAN star, then obviously it has a lot of this. It has to get the range somehow, and that is through lower data rate. So it will, in principle, has the same issue that LoRaWAN and Sigfox and others have. Yeah, I'm scrolling up a bit. Then we have the average latency per hop in RIIM. Yeah, it depends a bit on which mode you're running it in. In the single channel mode, it's about 50 millisecond per hop latency. And if you're doing this TISH, which is the very technical term here, but this frequency hopping with time slots, it depends how often you configure your time slots, basically. So if you have a battery operated mesh where you tune it to have like really low power consumptions in each mesh router, then you obviously have a longer latency. So there you can tune, you can trade off latency versus power consumption. Yes, so NB-IoT is we haven't really focused on NB-IoT here because it's a bit different business setup. Yes, and there are questions more about how that will turn out in the future. Yes, you have a subscription cost per year. What you get for that? I know that most of the offers higher subscription cost, but then you have some sort of service license agreement. What you get, then you have to compare that to managing your own network. So it's a bit difficult to say. But obviously, if you have one sensor or two sensors, the gateway suddenly become a lot, and managing the gateway becomes much of your cost. But I don't, to be honest, I'm not sure if you contact the cellular operators and want as a private person to or as a company to buy two subscriptions, if you're almost allowed to buy two subscriptions. So yeah. Yes, then we have a minor, yeah, high power. Yeah, this indoor range is a bit difficult to estimate. So obviously you can reach more than 50 meters indoor with RIIM high power. But the problem with indoor is that when you start, it's not the meters that matters. It's how many walls you have to penetrate and what are the thickness of the wall and what are the material of the wall. So that's what matters. So that means to say 50-meter indoor is kind of it's a ridiculous way of specifying things, because it all depends on the structure you're going through. Because yeah, the attenuation indoor is, of course, you have the range attenuation, but 50 meters going in the air is nothing. And then it depends. So I would, if I had a huge building of a 20-floor building with 1,000 square meters, I would, planning a network, just like concrete building, I wouldn't, that would be a first, having 50 meters between devices to get good solid range with few retransmission. I would have it as a starting point. So I'm trying to kind of move a bit away from the marketing people who would say, now we have measured 1,000 meters indoor, and that was like an very open where you had the line of sight and no walls. Of course, yeah, that is a good number for the marketing group, but it doesn't really bring the correct range for for a big building with a lot of walls. So I guess the answer indoor is testing. Get the development kit, test in the building where you want things to happen. Maybe you won't need to test it in more buildings to kind of get see how it differs between different buildings. I think was there more questions coming in? Was that it? do not see any additional questions here. So maybe you want to round up.
Yeah, it seems like that was the last question. So looks like you did a good job answering all of them, and we are about on time, so that's perfect. Okay, guys, that was really nice. I hope it was informative, and really thank you all for taking the time this morning to join us. And I hope that was interesting for you, and hope you learned something new. And please make sure to check the webinar recording after it's done, and make sure to check our document library. And by the way, this presentation was based on the white paper number 21, which goes into depth into all of these issues and points. It has more numbers, it has more details about this, so please make sure to check it out. It's white paper 21. So thank you all, and I wish you a very pleasant day. Goodbye.